organizers for the invitation. Okay, this is experimental talk, okay, on the search for electromagnetic fields and CME, heavy ion collisions with the CMS detector at the LHC. Okay. So the presentation is based on these three articles here. And first, I will start with a search for electromagnetic fields using elliptic flow of the zero mesons. Actually, in the case of the elliptic flow, will be a kind of search for Coulomb fields caused by the collision participants. And then after, I will show some details on the analysis of the CME search in the CMS based on these publications. Okay, just as an introduction about which are the tools I'm going to use here. So in heavy ion collisions, we have a kind of a standard model based on several steps to describe the collision. And around 1 to 10 femtometer per C, we expect the formation of the QGP. And one of the main observables used for the evidence of this QGP was the flow coefficients, for example, the measurement of the flow correlations. In fact, it's a very tricky measurements to do here. And the idea is basically that when you have a collision, for example, peripheral one, the spatial shape of the geometry or the fluctuations, quantum fluctuations, because of the configuration of the nucleons in the nuclei, they are translated to final state and are presented as a final state correlation. And this can be described as the by hydrodynamics using I mean the sorry, I forgot the here it's a plot that of this correlation as a function of delta phi and delta eta. So basically, the correlation related to flow is what we call the reach here. But what I'm going to show here is always non-trivial to measure this because we always have several sources of backgrounds, okay? And one of the more complicated backgrounds are jet fragmentation, what we call, usually we call non-flow. It comes from also resonance decay, but here is also have some short-range correlations that we call HBT, but we can also have some back-to-back correlations like dijets. So this is a kind of type of measurement that we do of this correlation that we call two-particle correlations, and we can project this in the high value of delta eta, and then this projection be parameterized as a Fourier expansion. And then in this Fourier expansion, we extract these flow coefficients that we call the VNs. So these VNs, they will quantify our correlations, okay? So, and then we usually call this second coefficients the elliptic flow, and the third one, the triangular flow. And the elliptic flow is mostly connected with this almond shape of the collision. It also will depends on the fluctuations of the nucleons, but the V3 is mostly related to the fluctuations. But we can also have several orders of VNs here, okay? So then in heavy ion collisions, we also expect the creation of very strong electromagnetic fields. And here on this plot, is on this paper, it's not a full magnetohydrodynamics calculations, but they introduce the magnetic fields in a perturbative way based on the book of the hydrodynamics evolution. And then to form a magnetic field, you have several components. So mostly from the expectators, the nucleons that don't participate on the collisions. But we also have a component, what we call a Coulomb component, based on the participants of the collisions. So, and then on this, I'll show you a reference that they show that these components, they can cause some additional contribution to this flow coefficient. So in case we have this non-zero electromagnetic field. And what is important in terms of the QGP, for example, characterizing the QGP, is that we can extract some properties like electric conductivity, drag coefficients on the QGP. Why? So if you have a QGP, for example, the lifetime of this electromagnetic field, it can vary. And in some studies, they can show that it will have some, it can have some deviations on the flow. So here, we call the delta average PT. That's related to what we call the radial flow, okay? The V1 is related to what longitudinal flow, and you have also the V2 and V3 also with effect from this electromagnetic field. They can be generated totally, one part generated totally by the effect from the electromagnetic field. So, so then what enters the D0 mesons? So D0 mesons enter because the D0 is composed by a quark up and charm, and the charm quarks with of its mass, it's produced in primordial stage of the collisions. So with a typical mass that they usually pass through the QGP, so they can probe the QGP evolution. But in this case also, since this magnetic field, it's very, it decays very fast, the magnitude, so it also can be present in the stages where this magnitude was very high compared to other light quarks where they are produced mostly in the QGP phase, so in a later stage. So that's the idea. So we expect that the signal, and there are some papers about this, the signals on the D0 influence from the electromagnetic field should be higher, okay? So in special, we have some measurements from delta V1. That's not from CMS, but from Alice and Star, based on these studies on the delta V1. And this is not experimental, this is just from the paper, theoretical paper, where this component is totally from the magnetic field, okay? So in principle, the main observable would be really to go to a V1 of the zero mesons. And I will not show this here because we have some problems with non-flow, okay, contaminations. But I will show here I studied based on delta V2, okay, that we expect some also deviations. Here is a plot for pions, but there is no calculation for D0s, but in principle we can expect also in the same way as happens with the V1, a higher magnitude for the D0, since it's produced, the quarks is produced in primordial stage. So what's the apparatus? Is the CMS detector. It's a general purpose detector. So, but the main components of this detector that we use is the silicon tracker. That's basically used to measure the charged particles. So I'll show you the D0 is constructed in the kaon and pion channel, okay? We have also forward detectors that are basically used for triggers, but also used for the measurements of the event planes of the, that we use in our analysis. Okay? So electromagnetic and the hadronic calorimeter is also sometimes used for high multiplicity events that we have in proton-proton and proton-lead collisions that I'm going to show here. Okay? So the D0 is reconstructed in the count and pion channel. Okay? It has a very small branching ratio, but in the CMS is the best channel to search for the, to identify the D0. So it has very small, it decays before the enters in any layers of the detector, but we can reconstruct the secondary vertex of the decay. So the CMS doesn't have what we call the PID. We cannot identify counts and pions, but we have all the charged particles. So basically, we loop over all the charged particles, combine all of the tracks, and do a kinematic fit where we can identify this D0 by looking at the peak of the particle because we know the mass of the D0. Okay? So here we use machine learning method to identify the D0 because we have several variables when we reconstruct this vertex. So, and we use this variable to separate from background, mainly combinatorial background. So you combine randomly the tracks on the identified, and then you need to separate this. Okay? Okay, so this is one thing important, that our measurement is for prompt D0. So non-prompt from, for example, B hadrons, we use as a systematic uncertainty. Okay, we now have a measurement for VNs for non-prompt. That's quite new from CMS. But here I will just talk about prompt D0s. Okay, so how we measure the VN? So VN, there are several procedures to measure it. I just illustrated one with the two-particle correlation, but you can use, for example, what we call a scalar product method. And basically, you don't actually correlate the particles, but you correlate what we call vectors. When we look at these vectors, you can think about like I'm correlating particles, but we use actually a sample of particles in different parts of the detector. So this scalar product expression, it will bring you the VN measured for each part. So we correlate the zeros vectors. That's called by a sum of this weighted exponential of the E phi. E phi is related to the azimuthal angle of the particle, and this weight will depend on each detector it's detected the particle. So if it's in the HF detector, it's a hadron Ford calorimeter, you use the transverse energy, but this is in the tracker, you'll be the PT of the particles, okay? So, and how we measure the delta VN? The delta VN is just calculate after the reconstruction, we can identify what's the zero and the zero bar based on the decay, based on the chart of the tracks. And then we calculate already in the level of the scalar product, the delta VN. So how we will extract the signal, because I said in the reconstruction, if you do this in practice, you see that we have a lot of background. So what we do is that this is basically background, and then the peak is here. But this was after the BDT, after the boosted decision tree, because before you cannot see any peak. So when we do this procedure that I said, it's basically something flat with a combinatorial background. But after applying some cuts on the variables, a cut-based variable, you can also find the peak, but we should optimize this to have a larger yield. So what we should do is you measure the VN. Here I have an example for V2 and the delta V2 as a function of invariant mass, and doing a simultaneous fit with the spectrum and the delta Vn as a function of the mass, you can extract the signal Vn. So the Vn of the D0, okay? So here's how we model this background, so I'll not go in details, but that's basically the general procedure, okay? So what we find when we measure the Vn of the D0, we see that it flows like the light hadrons, okay? It has a non-zero Vn, okay? And here's as an example as a function of PT and different centralities for V2 and V3, okay? So, but for the search of electromagnetic field, as in the theoretical reference, we should look at the delta V2 as a function of rapidity, okay? So, and when we measure this for D0 bar, we found these results, okay? So that is, in terms of the uncertainties, are consistent with 0. It's quite shifted, systematically shifted to some positive value, but without uncertainty, we cannot claim much than that. So the charged hadrons is expected, so the calculation that we have for charged hadrons is expected to be a negative with a sign flip here compared with our measurement, but we see we could get something already with a very small number, so for the delta of the D zeros. So that would be interesting to have some calculations to see how they can constrain on the, for example, electrical conductivity of the QGP, okay? Just to note that you had also measurements of delta V1 in Star and Alice. And Alice, they always, they see some deviations between the D0 and D0 bar. And interesting that the sign of the deviation is different, is opposite. So, and the Star follows the deviation from the theory, but in the Alice, no, they got the opposite sign. So that's interesting. As we are getting here, so it seems that we can have some dependence on the energy. That would be interesting to do. So, but that's basically the status here, okay? So, as you could see in the plot, what we should improve on these measurements. So, we need to improve all statistical uncertainties for sure, right? As you could see there. Systematic is uncertain, so that would be tricky. So you say to me, but you have a method, so if you improve your statistics, your systematic will be the same, so you are in trouble. Yeah, in fact, but we can improve the method. So one of these in this direction is, for example, our non-prompt measurement that we had. So we improved a little bit the way we extract the VN. We don't do anymore the mass fit. We do a different procedure, whereas we could remove the systematic uncertainty from this side. So that was very tricky to treat because we didn't know exactly the shape of the background of the VN as a function of the mass, that sometimes has some linear, sometimes has some polynomial, and it was hard to guess about the shape of this. And this introduced some considerable systematics. So at least in CMS, what we should try to do next. So in fact, it would be important to also measure together with Alice the delta V1. So for sure, that would be important. But using the HF detector, we cannot do it. Okay, so the no-flow effect on the V1, that's a pretty small coefficient. It's very hard to remove. Okay, so we need to use some expectator plane measurement. Where we can do, like Alice is doing, the delta V1, and this should be done for all the particle species. Okay, there are some interesting theoretical studies also based on the delta V1 of the leptons from Z boson decay. I put here, and I'm not entering details, but this should also be interesting to be measured. Okay, but again, it's V1, so I need to use the spectator plane. So sure, if people can talk to me after, we can discuss, or in the questions, about other ideas that we can try in CMS or in any other experiment at LHC, okay? So let's go to the chiral effect studies that we use. Here, I'm not talking about more the zeros, but the studies are based on unidentified particles, okay? So mostly charged pions, depends on the momentum, but we don't identify it. So then it would be pions, kaons, and protons together, mostly, okay? Okay, so how we, what's the signature of the chiral magnetic effect on heavy ion collisions? So we expect a charge-dependent correlation, okay? Some of the presentations already mentioned this. So we have some signatures from the chiral magnetic effect, okay? And I will try to show you here that what we learned from these studies, and also there are several studies from Alice and Rick, where that they show that this is a very difficult measurement because the background, thank you, because the background is very hard to deal with. Okay, so signature, we expect some kind of back-to-back emission of opposite sign charged hadrons, but a collimated emission of same sign charged hadrons. But the way that we can access this is what we call a three-particle correlation, something similar as I showed in the case of two-particle correlation with the scalar product. We can measure this three-particle correlation because it contains one term, that the parity odd term, that will carry the information that could be presented from the CME. Okay, so if we get this, if you get these observables and measure them in the nucleus-nucleus collision, this plot summarizes nicely this. So we have from CMS and STAR, and from similar kinematics. So they got similar results. Interesting, that's STAR with a different energy. They got similar ones, and they see a charge-dependent correlation. Okay, they see. Okay. But the question is this is really attributed to the CME, this large correlation that we see here, okay? So what is the strategy from CMS measurement is to measure this correlator also in the p-lead collisions, okay? In the proton lead. Why? So because in the proton lead, we expect that the B and the event plane are randomly distributed. So we expect the signal to be much smaller than in the lead, okay? So here is a Glauber model simulation, okay, for the lead and for the vector of the event plane, okay? And here for lead also in the correlation of these directions, okay? So then what we did, so we calculated this three-particle correlation. Actually, the plot that I showed before was for opposite sign particles and same sign ones. And here we got the delta to remove the charge-dependent backgrounds, okay? Charging-dependent, sorry, background. And then is what we got. So here is for P-lead and P-lead for lead going, because LHC, they run part of the data taking with the lead in one direction, and then they revert it in the other direction. So, but if we do, we always do, because since this can be dependent on the kinematics, etc., we always do in the two configurations, but we do also for the lead here in the same, of the same observable, the delta, gamma, or something like that we usually say here, okay? So we do this as a function of the delta eta between the two particles used in the correlator, but we do also in terms of charged particle multiplicity that we call N-track offline. It's a reconstructed tracks. So in terms of, based on these uncertainties, they are in principle compatible. You can look better in the data and see that probably there are some trends, but we would need some more precise results. But in principle, what we got was something that indicating that this effect was mostly from the background, because in the P-lead, we were not expecting a big signal from the CME, okay? So, but this was not enough to think about this. So what we did was we improved a little bit the method. We did some more details on this based on using a new observable that is more related to the background and follow this linear relation. And the idea was to, thank you. The idea was to find exactly what's the content of this background. So, and if there is a CMS signal, how we can quantify this in a more precise way, okay? So, in addition, this observable, that's basically from local charge conservation. That's one of the backgrounds, the main backgrounds that we expect to mimic the signal, okay? But we can also define one observable based on the not only on the second order event plane, but also in the third order ones that we don't expect even the signal there for the LED, because it's uncorrelated. It's weakly correlated with the Psi2. But then we measure this also for P-LED to cross-check. But the idea was to measure for 2 and see how it compares with the two systems, and guess more about the content of this background. Okay, so this quantity, when we divide this kappa, is basically a constant on this approach. Okay, and then in principle, a constant that will depend on the kinematics and detector acceptance. And then if we control very well these conditions, we are expecting this to hold in our measurement. So then that's what we did. We measured this to check if these considerations are following. What we did here is basically the measurements of this ratio. We did this for P-LED and for LED. So, and we did for the two observables with the n equal to 2, n equal to 3 for both. And what we got is that they got similar results, so with some systematic shift here. This is in terms of the charge particle multiplicity. But we have plots also for the delta eta, delta pt, and average pt. And they are also with similar trends as we are observing here. Obviously, this is basically kappa, but when we plot with the kinematics, it will not be quite flat like this. It will be more like a linear relation, okay? So another procedure is it's 1 minute, right? Another procedure is the event shape engineering method that we have used. Basically, we calculate what we call the Q2 quantity, where we can slice this, because this relation is basically a direct relation with the V2. If we slice it in terms of V2, we can test the linearity of this relation of delta gamma. Okay, that was the idea. So when we try to measure this, we see actually that one of the terms is not really flat. It has some non-trivial dependence. And then we do a ratio, We do a ratio to avoid this dependence, and then we got quite linear and pointing almost to 0. But I would phrase here that, there is no signal. No, it's very hard to say, because in principle we have V2 here that is non-trivial, measuring in low multiplicity and can have some non-flow. That's one of the points that we need to investigate more. So based on this 0 signal or signal small that we observe here, we do a 95% confidence level limit based on these assumptions that we are using in our measurements. So that's the point. So this can vary for sure. And then we observed a small probability to have the signal magnitude to be small compared with the background. So this shows some challenge for us, because show that the background is very huge and hard to control. Okay, so but there are plenty of measurements. So the next speaker will describe this in more detail, I think, and the other experiments also. Event shape engineering, isobar collisions, and also interesting the measurements with regard to a spectator and participant plan, where we see some indication of signals, but with a small significance. That would be very interesting also to do in the CMS when we have the RPD detector. So sorry for the delay. Thank you.
Okay, thanks. We have time for just one quick question.
Thank you for the talk. Can you go to page 20, please? I want to ask something about the plot on the left-hand side. Yeah. So I'm not sure I got this correctly, but red and the blue points should be identical, and their scattering is just a statistical noise, or is there something to understand there?
We expect that it's just statistical, I think. Yeah.
Okay, thank you.
They should be identical.
Okay, let's continue with questions on the coffee break.
Yeah.
And thanks again to the speaker. Please, next speakers, please send me your talks.